And the last thing we want to do today is just cast that Jeans mass in a slightly more cosmological footing. And in particular, we can look at a radiation versus a matter-dominated universe. And so, first thing we can note, flat universe, we have the energy density, the critical density, is 3c squared h squared over 8 pi g. Or, as a time scale, the Hubble time, which is equal to 1 over h, is just equal to 3c squared over 8 pi ge to the half, which is just 3 over 2 to the half times your dynamical time scale, which we had all the way back up here somewhere as c squared over 4 pi ge, and your Hubble time is just 3 over 8 to the half times that. So, if we substitute in for the Jeans length, then we get the following. And so all we need to do now to work out what lambda j is work out the sound speed. And so for radiation, W equals 1/3, and you'll recall again from back up here that the sound speed is just c times the square root of W. So we can write lambda j equals 2 pi to the 3 over 2 to the half 1/3 to the half c over h, which is approximately 3c over h. And what you can notice, this number, c over h, is the horizon size. It's how big the universe is. This is 3 times larger. So objects cannot collapse in a radiation dominated universe. And actually, this is the cause, I've already mentioned it, of these baryon acoustic oscillations. Things try and collapse, they expand again, they collapse, they expand again. It's exactly this. They're trying to make structures, but the pressure is pushing them back out. In a radiation dominated universe, that's what happens. In fact, it's not really the radiation domination that matters. It's actually this true while the matter is coupled to the radiation. I.e. when you have things like, E plus gamma to give E plus gamma, so i.e. before the CMB is emitted. And the universe ceases to be radiation dominated well before the CMB is emitted. But it doesn't actually start collapsing to form galaxies until after that. So after a formation of the CMB. You can't quite use W equals 0 here because, of course, there is still some speed. It's just much lower. We know that KT is equal to 0.26 electron volts. And the sound speed is roughly 10 to the minus 5C at that point. Rho baryon, this is actually all stuff you can get out of the cosmic microwave background, is about 5 times 10 to the minus 19 kilograms per meter cubed, so it's still not very dense. And MJ is now about 10 to the 5 solar masses, which is the size of a dwarf galaxy. So at this point, structures start to form. And this is also a slight simplification, because you can note, for example, that dark matter doesn't feel pressure. Experiments like the bullet cluster that we saw last week tell us that. So dark matter starts to collapse earlier. And so what you actually form is you form dark matter halos. That's what they're called, clumps of dark matter. Inside those clumps, you start to form stars. And once those stars light up, you have visible galaxies. And it's worth noting that these early stars and galaxies may look quite different to galaxies today. And so the very last thing I'll do, I've got some slides that I will actually go through on the computer to show you some sort of simulations and some sort of key features of early universe structure formation.